Hi again. This worked pretty well last time, so I'll do a little bit on the tablet, and then we'll switch to the slides, and we'll go from there. We're looking at chapter 7 with this, and again, when I was taking physics, this sort of thing was just presented like, here's the story. This is the equation. This is what it is. This is yeah, and then later, okay, this is what it does, which never felt particularly satisfying. I was always like, well, why that? So here we are. We looked at the pivot activity about a sliding puck coming to a stop. So suppose we're talking about not a yellow thing, but suppose we're talking about some surface and we have some object. And the object has some initial speed right now at this spot. It has some initial speed and it's traveling to the right. And as it slides, friction acts and slows it down until eventually, sometime later, it has stopped. Now, that takes some distance according to how strong friction is. But here's the thing. Suppose we do this again. Faster. If we have it, we know this because we did the experiment, right? A greater initial speed will mean that we travel farther before we come to a stop. So eventually, by the time we come to a stop, we'll be over here somewhere. Farther. I don't know. In the same distance that we traveled before, on average, we'll be going faster because we started faster and we haven't stopped yet, which means we're going to cover this much distance in this much in a lesser time than before because we're going faster. So to travel that distance requires less time, which means because remember the force of kinetic friction, which is the coefficient times the support force, doesn't care how fast we're going. It has one value, which two surfaces and how heavy is this object. So the impulse force times elapsed time is less for the second trial. Same force, but less time because we're going faster. That's a little bit odd. we slid the same distance over the same surface, but the second time, that force imparts less impulse. Even though the acceleration is the same, it takes us longer to come to a stop. The acceleration's the same, the distance traveled is the same, and if those two things are the same, then the difference between the initial and final square speeds is the same as it was in the initial case when we were started a little bit more slowly, because of that acceleration equation that we developed a couple classes ago. We said that the distance traveled was related to the acceleration and the square speeds. So same distance, same acceleration, because friction is friction. Same difference in the numerator here. The speed that we have here versus the speed that we have here, if we square them both and subtract them, we'll get the same answer whether we were talking about the original case or the faster case. That's impulse is different, but this story is the same. And that's weird. And it makes me feel like maybe we can tell a slightly different story. Maybe impulse and momentum aren't the best the best tools for this particular job. What appears to be the same is not the time that we spend acted on by friction, but the distance that we slide along the surface. What if, just hypothetically, instead of force applied for some amount of time, which we said was impulse, remember? What if instead of that, we said instead force times distance? The times are different, but it's the same force, the same acceleration, and the same distance traveled. Same square difference between the speeds. So talking about the time, that's different, but it doesn't match with all the other things that are the same. Force and distance are the same. And so is the difference between the square speeds. So maybe there's something to this idea. Instead of talking about the total effect of force over time, what if we talked about the total effect of force over distance? I'd like to call that work. So if we talked about the net force, that acts for some distance, we could call that the net work, the sum of all the work, I guess. What would that relate to? Well, net force is, according to Newton's second law, mass times acceleration. And then we still have to multiply by the distance. But acceleration is change in velocity over change in time. Now, we're multiplying a number times a fraction times a number. We can do this in any order. And in fact, we could do this division, distance divided by elapsed time, and then multiply by the change in velocity. But the distance divided by the elapsed time, that's exactly how we defined average velocity. Change in velocity, average velocity. The change is the final minus the initial. The average is the initial plus the final over 2. And you've seen this trick before because that's how we ended up where we ended up with our equation. Our kinematic equation, where we distribute through the binomial, we've got a FOIL, and we end up with the difference of two squares. Call me crazy. Before, we ended up with something that looked like mv final minus mv initial. And we said, hey, that looks like delta mv. Okay. How do we get rid of that? All right, well, what if we do the same trick here? That looks a lot like the change in some other quantity. One half times the mass times the square speed. We evaluate at the end, subtract what we get when we evaluate at the beginning, and that's the total change in that thing. And that is apparently all related for some reason. Well, Newton's second law is the reason. It's all related to the net work. If we'd say that work is force times distance as opposed to impulse being force times time. Just like we did with momentum, I'd like to give this thing a name. Let me write it with better penmanship here. I'd like to call it kinetic energy. And I'd like to stop using handwritten notes at this point, and I'll switch to slides, and we'll sort of rehash some of this stuff that we just wrote down. I know this was quick. Please do rewatch this. But this is the why would we define work the way that we did? And what does that have to do with kinetic energy? Well, now we can see it. All right, on to the slides.